Hello, my name is Hajime SAITO. I'm from General Robotics. Today I'll be presenting what changes we've made to OpenHRP to make it more accessible to developers. So this is an overview of my presentation. I'll show where the OpenHRP came from, what it's composed of, and what we tried to change to make it more accessible, what we did, and a sample to show you how to actually deploy the system itself, and then I'll end with a summary. Well, OpenHRP was a product from the Humanoid Robotics project, which was run from 1998 to 2003. The products were, on the hardware side, the HRP series robots, and on the software side we got OpenHRP2, which was the simulator back then, and also the controller. And well, it was a shame to waste these products. General Robotics was made to actually commercialize them. And since then, HRP2 has developed to become HRP4. And OpenHRP2 was initially open, just meant the specification and interface were open. It wasn't actually open source. And we got a lot of complaints by people who tried to use it because they couldn't actually see what was going on inside. So there was a different project which was started to actually make the source open. A lot of it was very difficult to read, which was another reason we couldn't actually open the source back then. And since 2006, I think OpenHRP 3 has been open, but it's mainly available from the AIST website, and it's just a bundle of source code that's updated annually, and there is documentation, but it's mostly reference-based. So if you really know what you want to do, you can use it to check that you got things correct, but otherwise people starting out had a bit of a problem. And well, basically when people ask, when people answer the question what OpenHRP is, everyone says it's a dynamic robot simulator, and it's distributed. It uses Korba to actually link the components, and a few arrows are missing, but the simulator client actually communicates with the model loader, dynamic simulator, and the controller, which has since been shifted to use OpenRTM. But actually, if you look into this, there's a lot more going on, because AIST actually made the components to be libraries. And although they have this thin skin that requires the use of Korba, the libraries themselves are made very well. And we actually use the libraries more than the simulator itself to actually create the controller components that KAWASUMI actually introduced in the previous presentation. So this is the main thing for my talk. I think will be that OpenHRP is nice to use if you can get Korba running, which happens to be a big problem for most new users. But if you look into the source code, the kinematics libraries, the model libraries, and collision libraries are very nice, and we thought that perhaps there's something that can be done to make them more easier to use for outside users. So one of the problems I thought was that the annual update, which was erratic, it wasn't actually based on a schedule, it was just updated when there was something necessary to update, which doesn't really help if you want to base your development on it. There were some problems we had with some robots that we tried to implement the control system to, because we had to use the convergence-based inverse kinematics, which is very useful, but it's the default that's provided by OpenHRP. We had another problem with multiple data files. This is sort of an internal problem for us, which was based on the fact that they used VRML to store the data, the model data for the robot, and the documentation itself, as I said before, was mostly reference-based. So what we decided to change to perhaps make it more easier for other people to use was to open a revision control system that users could see and see what kind of changes were being applied, what kind of direction we were trying to take the software. And by we mean this General Robotics. We do see what EIST is doing, but we also have to apply some things that our robots need. And it's not always easy to get that source back into the main branch because EIST themselves sort of rely on the source code, and it's difficult to actually get the testing process in. Another thing was we really need an analytic solution for inverse kinematics because we actually use this within the control loop of the robot. And we have so many problems with data files, especially when users need to use them, because sometimes they require checks to see that they don't actually interfere with each other, or you have different settings in different files. And we actually have users. We have users of our robots, so that we are sort of gradually, really gradually accumulating some documentation that users can actually use to get themselves familiar with the OpenHRP software. So this part was easy. AISP releases OpenHRP using EPL, which allows you to use the source code so long as you actually feed the changes you made back to them. And if it's all open source, they can pull it themselves, and also they can check it out. We decided on Google Code because I'm a big fan of Python, and I wanted to use Mercurial, and they were the only at that point that I checked, were the only people that actually allowed you to share code using Mercurial. We have another mailing list that we have for our users, and we have added support for KAWASUMI, which seems to be very extensible, and this was something that Rosen actually told us was really good to use, so we sort of added that support to OpenHRP. We want to change things like callback name handling, things like that, but this will come later. So this is basically the main thing. We haven't actually switched from convergence-based inverse kinematics because it's still in the code. However, we have, after talking with Rosen and finding out about OpenRave, we have been able to use the fast IK functions in our robots. And so, but before that, I think I'd better tell you what kind of configuration files that are actually needed by the system itself, before I show you how we sort of linked OpenRave with OpenHRP, well, loosely linked. OpenHRP uses VRML, and VRML has joint configuration, joint angle speeds, and joint speed limits, and surface data. On the other hand, if you really want to control a robot, you want to divide that robot into parts, like arms and legs, because you're not always controlling all the joints at once. If you are generating joint trajectories, then you are controlling all the joints, so you don't really consider that. But if you try to do something like cell-based construction of parts and more industrial applications, you usually have to do something that controls one part while another part of the robot does something else. So parts are very important, and this was what usually caused a lot of problems. And also the controller deployment themselves is usually a problem if you have something like a product, because it's a system that has to boot up itself and it has to run itself. So this is, well, I think this is pretty obvious. I'll go to the next slide. So OpenRave uses KAWASUMI, and KAWASUMI itself has joint configuration, and most important, it has the part configuration. And so looking at this, we first created a VRML to KAWASUMI converter, and that allowed us to use OpenRave and actually create an analytic IK that can actually be fed back into the OpenHRP controller itself. This was very useful because now we have we aren't restricted by the actual model itself. If OpenRave can generate the analytic IK, then that robot will have an analytic IK that you can use in the real-time loop. Well, but if we have the part information inside the data file itself, it seemed a shame to actually have to go through OpenRave each time to actually do this, because we needed the part configuration inside the OpenHRP controller anyway. So we put a front end to actually convert and import KAWASUMI into OpenHRP. And that was very easy because OpenHRP is very modular, and all that was required was to create a front end to the model loader to actually do this. And another thing was that as OpenRave is open source, you can actually see how to use the fast IK and also how to load KAWASUMI itself, because it's a very good example. And so we have these in place. The only thing that's missing right now is the controller deployment. This was what was missed actually when I was writing the paper for this presentation. I sort of noticed this yesterday as I was preparing this. But the controller deployment itself, as we use OpenRTM, I think if you saw the first presentation, OpenRTM uses YAML, and I think there should be a way to actually add that to KAWASUMI as an extension somehow, and actually combine it into one file. Documentation, I think, is still, it's always a problem, but we are sort of getting there. But mostly, as it's open source, we're sort of relying on that at the moment, which is not very good. But as the NIDO project gave us a boost in the number of users that actually use OpenRTM, the OpenRTM controller, we are sort of starting to gather some information, and we have help, external help, to actually get that documentation into place. Next, I'd sort of like to show you how OpenRave and OpenHRP can actually be combined to create or do a rough checkout of a robot. If you have a KAWASUMI model, which is a bit of a hurdle sometimes, but there are exporters for real CAD systems for KAWASUMI. So if you're able to get that, or if you're able to use that, then the rest isn't too difficult. It might not sound that convincing, but the things that you have to add are only the speed limits, center of gravity and mass, if you need dynamics. But otherwise, it's the joint configuration itself which is in the file, and joint angle limits which you have to just add in the right place. And so that's the only real hurdle that's there. There's a high gain controller that's included in the OpenHRP package, and that accepts joint trajectory files.